Okay, we're recording. Okay, so here's what we were talking about last time. We were talking about equations and polar coordinates. We already did these two examples, and the big idea is that you can use algebraic relationships that we already have between polar coordinates variables and rectangular coordinate variables to effectively convert, a polar equation into a rectangular equation. Now, sometimes you have to do a little sort of cleverness in advance, right, to make everything fit. But no problem. Okay. All right. So moving along. Now, this next example, a little bit more trouble if you try to finesse this equation around to where it's something where you can just sort of recognize the rectangular equation. You're going to lose. It's not going to work well. So here you can resort to the tedious method of just plotting points. Right? So now you could do one point at a time, but I like to do sort of ranges of values all at once when you sort of know what's happening. So in particular, let's start off thinking about, as we rotate through the first quadrant, starting with theta equals 0 and moving around to where theta is equal to pi over 2. So for this range of values of theta, what's happening? Okay, now keep in mind, theta is our polar angle, but it is not the argument of the sine function. The argument of the sine function is 2 theta, right? So 2 theta is not going from 0 to pi over 2. 2 theta is going from 0 to pi, because, theta is going from 0 to pi over 2. So the question we want to ask ourselves then is, what is happening to the values of r? What is happening to the values of r as 2 theta, as the argument of the sine function, let's think of it that way, as the argument of the sine function goes from 0 to pi. And of course, here's a familiar picture of what sine does between 0 and pi. Starts at 0, goes up to 1, comes back down to 0. So this is your little guide here of what values to do for r as theta is ranging from 0 to pi over 2. And keeping in mind then, as my direction goes from here to here, my, if you will, distances are going to start at 0, then increase up to 1, and then go back down to 0. So here we go. Starting in the theta equals 0 direction, right? Our distances are small, and then as I turn, these distances get bigger and bigger. Note that they get as high as 1 when I'm halfway there. And then from that point proceeding, my r values get smaller and smaller, approaching back down to 0. So in some sense, you might say that this kind of, if you will, curve here, sort of in polar coordinates, ends up looking more kind of like that. Everybody with me? Kind of see the strategy and the pattern here? Let's look at the next range of values. What happens as theta now is going to go from pi over 2 to pi. Well, keep in mind, that's what theta is doing. That is not what the argument of sine is doing. The argument of sine is going from pi to 2 pi, for which values r, namely sine of that argument, is going to start at 0 and then go all the way down to -1 and then proceed back up to 0. Now, this one's a little bit weirder because as my theta goes over these values, notice that the r is going to be negative. And that means that as I'm, for example, pointing this way, right, the r is going to tell me how far to go back in this other direction, as it were. Right? So, again, a little bit creepy to think, but so for example, for a value like that, for that value of theta, we're going to go back a negative amount as indicated by the value of r, thus putting me to a point such as here. And with that in mind, let's see here, eraser. With that in mind, I do kind of like this. and thus the curve that looks like that, if in some sense, is going to do like this as polar coordinates in the xy plane. Everybody okay? So that's the same basic strategy, different details interpreted accordingly. Okay. So I'm going to leave it as an exercise. I think this is a healthy exercise for everybody to work out for themselves as to what happens next. As our angles, we've already talked about first quadrant, second quadrant, what happens as you proceed through the third and the fourth. And you can probably guess, right? You can kind of see this sort of thing happening. You could probably guess that it would do something kind of like this. And in fact, that's right. But good to think through the details. Again, it's good little mathematical weightlifting. Think it through, persuade yourself, and in fact, it's kind of a four-leaf clover kind of little shape. Okay, does everybody buy it? Is everybody happy? Okay. All right. Okay. Sometimes the algebra is a little tricky. We've already seen that if you have r on one side of the equation, a pretty neat move is to square both sides of the equation, because after all, r squared is something that we recognize, and we've benefited very nicely from that. Isn't that great? Here's the thing. If you square both sides of this equation, the right side would turn into cosine squared. That's not a thing in rectangular coordinates, right? I don't know how to write cosine squared in rectangular coordinates. So be aware, sometimes it's a different little trick. And here the slick move is to just multiply both sides by r. You still get the r squared that you wanted on the left side, just as you had wanted. But then you also, very conveniently, get r cosine theta, otherwise known as x, on the right side of the equation. And now we're into rectangular coordinates, and recognizing what this is just a matter of doing what's called completing the square, which I imagine y'all have seen at some point in the past. And if y'all are anything like every other multivariable calculus class I've had in the last, not say how many years, you have forgotten how to do completing the square. If that's the case, no problem. It is, after all, just kind of an Algebra 1, Algebra 2 thing. So look it up, right? I'm sure it's all over the internet. And if you're not happy with what you find there, come to my office hours, please. I'll be very happy to walk you through the details and the rationale for how to do completing the square. But it is a very useful algebraic skill, such as, for example, here. It allows us to turn something that we don't really recognize, right, into something that is very obviously a circle. Yeah?
Can you explain again why you can't have cosine squared?
Well, it's not that you can't, it's just that I don't know what to do with that, right? So in terms of converting that into rectangular coordinates, I just don't have any formulas that say, oh yeah, cosine squared, that's the following nice formula. So yeah, it's not that you can't, it's that you don't want to. Yeah, yes.
How did you get x squared plus y squared equals to x?
How did I what now?
Get x squared plus y squared equals to x.
Yeah, so everything on the equation on the left here, like this, it's just an established identity between polar and rectangular coordinates, right? And then this is one of our conversion formulas as well, that x is our cosine theta. So it's just recognizing known relationships. All right. Okay, sometimes it's easier than that. And going from rectangular to polar tends to be pretty straightforward. You basically just plug in x equals r cosine theta, y equals r sine theta, and just kind of simplify. It's very straightforward, very convenient. There are some kind of opportunities where you get lucky, though. Notice I did not immediately plug in the formula for y, r sine theta. The first thing I did is I sort of squared out this squared term here, right? So I can see all of my individual terms. And the reason for that is very often you get lucky. And you notice here, for example, because I squared that out, I immediately see not just x's and y's, but I see explicitly x squared plus y squared, which we already know is r squared, right? It's one of our pat relationships. in polar coordinates. So boom. So now this is not getting you to a different answer than what you would have gotten if you had just sort of, blindly sort of plugged in the formulas. But it saves you writing down a bit of trig that would then simplify to exactly the same thing. Sure, right? This is just easier in this case. And then, of course, there is a y left over, and that you've got to just write down the conversion formula. Okay. Alrighty. Okay, moving along. So that's polar. Let's talk about cylindrical coordinates. It's a different coordinate system. A lot of people like to call this polar coordinates in space or polar coordinates in R3. I think that's fine, I suppose, but it's also easier to describe as just it's cylindrical coordinates. Right? So I encourage thinking of this as cylindrical coordinates, but it remains, and it's very importantly the case that what we're really talking about is that for the x and the y in 3 space, you just do the usual polar coordinates stuff. It's literally the same as polar coordinates as far as x and y are concerned. The only thing that makes this different is that this is a coordinate system in space for points that have 3 coordinates. Right? And so there is the little matter of what about z? And well, z is just z. The rectangular coordinate z is also a cylindrical coordinate too. So yeah, as far as what's happening and where's the action in cylindrical coordinates? Yeah, it's polar coordinates, right? Just applied in a different context. All right. So a couple of quickie examples. If you say r equals c, keeping in mind that r represents a distance like that, setting that equal to a constant, incompetent art aside, always gives you a cylinder. That's the name cylindrical coordinates. Believable, I hope. Is everybody happy with that? All right. Alrighty, let's see here. How about a sphere? Now, this is the equation of a sphere centered at the origin in rectangular coordinates. Right? How would I convert this into cylindrical coordinates? Well, everywhere I see a rectangular variable that isn't a cylindrical variable, I've got to figure out how to convert that into cylindrical. So conveniently in this case, I don't have to plug in x equals and then separately y equals. We got lucky here, and x squared plus y squared I can convert as a bunch, by its as a single thing. That's just r squared. And then of course z is already a cylindrical coordinate, and so I can leave the z squared. Doesn't hurt anything. And so this leaves us then with what we call the cylindrical equation. Yeah.
Sorry, do you mind explaining what C is?
C in this case would just be the radius of whatever the sphere is. So if you look at what this equation here says, the left side says distance from the origin. Distance squared from the origin, right? And so basically this equation says distance squared equals c squared, which you could reinterpret as distance equals c. Yeah. I saw that hand back there first, sorry.
So with this interpretation,
yeah.
Spheres are just rounded cylinders, over the top, like the z, since it's a function, it's just not flat.
I guess I'm not following. Say again, please.
So in order to get the equation for spheres,
yep.
You use cylindrical equation to z also as
yeah.
A squared term, which is kind of rounded. Is that
I mean, I guess I kind of see what you're saying. I would call that maybe an intuitive satisfaction with the result we've got, right? But if you want to justify, why is this the equation? I think the best way to see it is, well, I already know that this is the equation in rectangular coordinates, and I can just convert, right? So, yeah. So think of what I would encourage thinking of what you said as kind of a satisfaction after the fact, Does that make sense?
Yeah, like not an explanation to get to the point, but like this
Right.
makes sense because of this.
Yes, yeah, that's why you're happy with the result. Yeah, yes.
So when you say right above R equals C is always a cylinder, is that
Yep.
if you were holding like a constant radius and then varied Z and theta and it would just draw?
Yeah,
Okay.
yeah, totally, absolutely. Yep. Right. Okay, now here's a tricky one. Z equals KR. I claim this gives us a cone. There's a couple of nice observations to be said about this. The first observation I want to make about that equation, first of all, this is a cylindrical equation. R is a cylindrical variable. Z is a cylindrical variable. It's also a rectangular variable, but whatever. It's a cylindrical variable too, right? So this is, in reasonable fairness, a cylindrical equation. And furthermore, theta is not showing up. Right? And so you remember how we were talking about if y is not in the equation of a plane, well, then the y doesn't matter, and you get something that's parallel to the y-axis. Or you might say it differently, all the cross-sections look exactly the same. Right? If y doesn't matter, then you can set y to be whatever you want. You always get the exact same picture. So likewise here, I can set theta to be whatever I want, and I always get the exact same picture. So what does that look like geometrically? Well, first thing I'll observe is there's Z equals KR. I mean, Z is just a multiple of R. You're going to get a line like that. Okay, but that's valid for any value of theta. So here's a value of theta. Right? For that value of theta, the cross-section of my surface looks like this. It's a line. Now, here's a different value of theta. Let's see here. If I were to let theta go a little further around, right, for that bigger value of theta, what does that cross-section look like? Well, it looks exactly the same. Right? So you might say, and I think this is a good way to think about it, when theta is missing from a cylindrical equation, all your theta cross-sections are identical, and therefore what you have is a rotationally symmetric surface. All the rotated cross-sections are all the same, and so it's rotationally symmetric.
Is that how you would interpret the previous examples, like R squared plus
You could.
squared equals C squared is like a circle, and
Yeah.
then you rotate it, and then
Sure.
the previous one is like a line, and then you rotate it.
Perfectly reasonable way to think about it. Absolutely. Yeah. So let's think about what does this actually look like then? And again, here's Z equals KR. By the way, some people get weirded out by this because some people reason as follows. See if you can catch the mistake. R is the distance from the z-axis, so it's got to be positive. So shouldn't that mean z's got to be positive? So what's going on with all this down here? Did y'all catch the mistake? I said R was a distance. It's not. It's a coordinate. R can totally be negative, right? And so sure, it's a little bit weird to think of points down here as being part of Z equals KR, but take this point right here, for example. That's got a negative Z, right? It can also be thought of as representing a negative value of R for a value of theta like that, right? R is negative, getting me right over where I'm supposed to be. That cool? Okay. Erase. There we go. Okay, moving along. A couple of little details here. You do have to be careful with your choice of variables when you're describing things, labels that you put on things. You just got to keep in mind going forward that R is now a coordinate, and it's, dibs has been called. R is not up for grabs anymore to be, the arbitrary name that you choose to represent the radius of whatever round thing is in the picture, right? R is now a coordinate variable taken, right? So when you have something else in the picture that's round, as is very often the case, just don't call it little r. I like using capital R. Great choice. All right. If you want, you could say like R naught, that's also fine, and various other variations like that. But don't forget, there is an entire rest of the alphabet that you're also welcome to use. Entertain using things like A and B and C instead of R naught, because again, that could, it's a little confusing perhaps. The analogy here is imagine doing business in rectangular coordinates, and you need to represent, let's say, the distance from a certain thing to another certain thing. I'm going to put it at an angle so it will look familiar. How would I label this distance? Well, I can call it almost anything, but I really shouldn't call this distance x. X is a variable. It's a coordinate variable. If I call this distance x, then I'm also using x to represent the x coordinate. I've got a confusion of variables. That's not okay, right? So totally analogous here. Try to avoid using R as a label for anything other than what it's supposed to be. Okay, spherical coordinates. So these are a little weirder, a little harder to visualize. There's some subtleties we have to be careful about. I am going to, as I have done already, commit some little math crimes and then confess and make up for it, right? So anyway, here we go. Spherical coordinates. They are rho, phi, and theta, as I have drawn here. Oh, by the way, you're going to learn a little bit of Greek alphabet in this class, unavoidably. So this little thing here that looks like a P is not a P. This is the lowercase Greek letter rho, and you can't write a P. A P is a different thing. And so it's annoying because y'all all have fantastic levels of practice in writing P's, right? But it's not the same thing as a rho, right? So you got to make sure not to put the little, the ears, right? Don't put the ears on it, right? That's importantly not okay. All right, so now this is silly, but believe it or not, when I was in college and the very first time I had to start writing a lot of rows, I actually, it's a little bit humiliating even, but I actually sat there and practiced. Like, okay, am I gonna be a spiral in kind of guy or a spiral out kind of guy, right? And you can decide for yourself who you want to be, right? But practice, and I think I probably wrote 50 or 60 of them, just trying to, I need this to look decent, right? And to not be a P, right? Etc. So you'd be surprised how little time it takes to actually clock a bunch of practice on that. Okay. All right. So here we go. Let's talk about how spherical coordinates work. We'll start with theta. Theta is exactly what you think it is. It's just like the cylindrical theta. It's angle measured off of the positive part of the x-axis in the usual direction, which, if you think about it, defines a half plane. As I like to say, hinged on the z-axis. So it's like the z-axis is a hinge, and you can think of this half plane as being like a door that hangs off of that hinge, right? Just like a door. Okay, so everybody good so far? Yes. All right, cool. All right. Okay, next thing. So what is phi? Phi is another angle. It's measured off of the positive part of the z-axis and kind of turns, if you will, toward the theta half plane. So that's why I think it's important to think of theta as defining a half plane. That's the indication, that tells you which direction theta points, right? As theta increases, which way do we go? It goes into the theta half plane. And notice that now that defines a direction. All right, so between the two of them, with theta and phi given, that gives me a direction coming out of the origin. Everybody all right? Yep.
How would you define a half plane as being different from a plane?
So a half plane, imagine I take a full plane and then I cut it by some line, right, and throw away one half. What remains is called a half plane. Is that cool? Yeah, and that's all that's going on here. So when I draw this what I have in green here, what I'm intending to suggest is that this extends infinitely that way, and infinitely this way, and infinitely downward. But it stops at the z-axis, right? So it's literally like half a plane. Okay. Yeah. Sure. Okay. All right. Okay. Now I just glossed over a detail. Let me fix that. What happens if phi is negative? Right. Well, this idea that phi is always measured in the direction of the theta half plane. Well, yeah, true. Which means that if theta is negative, that would just have you going the other way, right? So just like when we were talking about r, well, it could be negative, you just go the other way. Likewise, if phi is negative, you just go backwards. So you'd be rotating away from the theta half plane, off of the positive part of the z-axis. Yep?
The phi, where does it go to? Is it like a point on the thing?
Well, no, it's an angle, right? So you can think of a direction as being indicated by like a ray, right? And so what I'm saying is we're gonna start pointing straight up, and then phi says how far do I change the direction that ray is pointing, right? So being an angle, that tells me how far to change the direction. Is that cool? Okay. Okay, so that's theta, that's phi. And now, again, we've made the observation that between the two of them, with a theta and a phi, that defines a direction, like so. And once you have a direction coming out of the origin, then all we need is an indication of, I'm going to, again, commit a little math crime, how far we're going to go in that direction, right? And maybe we go that far, thus putting us at then a point. And that then is the point with those spherical coordinates. Right, so theta and phi define a direction. Rho says how far, air quotes, to go in that direction. And that puts you at a point. So now let's talk about the air quotes. Again, I have to confess to my little math crime. I was referring to rho as if it's a distance. It's not, right? Rho is a coordinate. I have to allow for the possibility it could be negative. There's nothing wrong with rho being negative yet. Right? We'll deal with that later. So if rho is negative, then yeah, fine, just go the other way. So let's see here. Let me clean up my picture. There we go. And yeah, so if rho is negative, you just go backwards like that. Everybody all right? Okay, so how do you keep track of these variables? What is the relationship between them and rectangular coordinates? I'm going to zoom out so we can fit all this in. I'm going to draw your attention to this little triangle right there, which I'm going to recopy down here for just kind of aesthetic purposes. You might not have this problem. Maybe you do, maybe you don't. In general, I just think it's a little bit easier to understand the geometry of a flat thing if we're looking straight at it. Whereas this, up here, this picture of this flat thing, this yellow triangle, I'm kind of looking at it at an angle. This right here is a right angle, but it doesn't look like a right angle. It's just kind of confusing, right? So I like to recopy things so that right angles look like right angles, and I'm just looking straight at it. I don't know, I just think it's a little bit more satisfying, a little bit easier. So that said, notice that our cylindrical coordinate r is just one of the sides of a right triangle, where the hypotenuse is rho and the angle is phi. And so with that noted, check it out, easy formula for r. R is just rho sine phi. Easy little trig. And then likewise, notice that, let's see here, Z is the other side of this right triangle. Again, easy trig, rho cosine phi. Everybody on board? This actually tells us everything that we need to know about conversion formulas for spherical coordinates. Because, well, what do I really need? I need formulas for x, y, and z. Well, one of these is literally one of those formulas. There you go. It's literally the formula for z. And the other one is exactly what we need to convert the formulas we already have. We already have that x is r cosine theta and that y is r sine theta. Right? So presumably y'all have already digested and memorized x equals r cosine theta, y equals r sine theta. Okay, cool. Just remember the trig of this little triangle, and now you automatically know the formulas for spherical coordinates. Yeah? For whatever it's worth, and I know everybody's different in how they learn things. I am myself no good at memory. I can make myself do it, but then 2 weeks later I don't trust my memory of it, and as experience shows, I should not. Right? So I don't like memorizing things by rote, and in particular this trio of formulas, I do not have these memorized. I never have. Right? And so I got through an entire second major in physics in which spherical coordinates are huge, right? Without ever memorizing these formulas. When I need these formulas, I think about this triangle, right? And the trig of this triangle, of course, is snap. I mean, there's just nothing to it. That's no problem, right? And then boom, I've got what I need. Everybody on board? Okay. Alrighty. Yeah, let's see. Let me zoom back out here, and let's look at this next example. Again, we have a Pythagorean relationship between rho and x, y, and z. Right? Matter of writing down some little right triangles and Pythagorean identities. And so if you want to talk about the equation of a sphere, that's actually really easy. There you go. Rho equals constant always gives you a sphere in spherical coordinates. And again, this is the motivation for the name spherical coordinates. Okay. Here's a tricky one. I'm going to leave some of this for y'all to work out on your own. Let's suppose that we are interested in this point right here. Obviously, there's some geometry to be worked out here, and I think it's pretty easy. You see various right triangles in this picture, and I think these numbers that I have indicated are pretty easy to motivate. So make sure you can think all that through. And with all of that motivated, let's talk about what are the spherical coordinates of this point. So recall, when we were doing polar coordinates are not unique. And even ignoring the whole, you can add 2 pi to any angle and nothing happens, right? Even ignoring that, there's still kind of sort of the 2 different ways to write polar coordinates. You've got the one where theta is pointing at the point and r is positive, and then there's the one where theta is pointing away from the point and then r is negative. Right? Well, there are 2 angles in spherical coordinates, and each of them gives you kind of 2 different options. So altogether, there's actually 4 different ways to write spherical coordinates for this point. And again, when I say 4, I mean that's still ignoring all of the, plus any multiple of 2 pi, which you can always do. All right, so let's talk through a couple of these. Notice at this point, I could think of theta as being pi over 3. Right, we've already talked about, I've already waved my hands at there being some trig that you can do to persuade yourself that this angle is pi over 3, so that's an option. Right? But there's a whole different way of thinking about it, and the part that I'm going to leave for y'all to work out on your own is that you could go all the way around this other side, and that is where theta is pi over 3 plus pi, right? In other words, going all the way around to where theta is in some sense pointing in the exact wrong direction. And then, for example, with the theta plane going exactly the wrong direction, you could talk about what would happen if phi were negative. And that would get you going exactly the direction you want to. Right? So, good little bit of mathematical weightlifting. Think that through, the business here about that I have in blue here, about 4 pi over 3. Let's talk through this part where we have theta being pi over 3. I could think of the angle phi as being pi over 4, kind of as indicated in the picture. Works fine. That gets me pointing in exactly the right direction. And then there's just a question of how far do I go in that direction, and then rho is just whatever that distance is. In this case, positive because, well, it's the direction is the right direction. And there's another possibility, though. I don't have to have my phi getting me pointed in the right direction. I could have my phi pointing in exactly the wrong direction. Now, just as a reminder, that's the right direction, if you will. But what if phi, again, measured off the positive part of the z-axis, and keep in mind positive phi means that way. That means that negative phi would go that way. And I could talk about going in that wrong direction all the way down to where I'm going like this in exactly the wrong direction, and then just choosing a negative value of rho would get me to where I want to be. Right? Everybody see that? Now, this angle here being pi over 4, let's see here, this being pi over 4, I think you should be able to persuade yourself that this, and let me clean up my picture a little bit. This angle here then, well, this little red angle of pi over 4 and this blue angle, grand total, that makes a pi, right? And so think through the positive and the negative and stuff. And this value of phi down here is negative 3 pi over 4. Everybody buy it? Some geometry to think through there, yeah.
Does phi have to be less than 90 degrees?
No, there's no such rules. No, phi can be any value. And now there are some values that are more convenient and desirable, right? But there's no real rule. So here's phi equals 0. Phi goes all the way down to pi and could keep going and could keep swirling around, or could go negative, and could, there's no restrictions. Yeah. In practice, it would be pretty weird to choose anything other than the obvious desirable values. Yeah. All right. Okay, so a lot left to think about on that one. Yes?
So is the third coordinate there theta, or is like the pi over 3 theta?
You're talking about...
what is that 2 doing?
This right here?
Yeah.
These are the rectangular coordinates. And you know what? Shame on me for not indicating. What I should have said is x comma y comma z equals this, and my lack of doing it is why you weren't clear. So persuasion by counterexample. Do as I say, not as I do. Is everybody happy? Okay. Yes.
Does it matter if theta is the angle from the x-axis or the y-axis?
Oh yeah, it really matters. It's x-axis. X-axis. That's the overwhelming standard. X-axis. Yeah. Okay. All right. Here's a neat fact. We all live on the surface of the Earth, and we describe locations on the surface of the Earth regularly, right, with longitude and latitude. If you're not familiar with longitude and latitude, the big idea, and I'm going to talk here about east longitude. East longitude is measured like so. By the way, just to put everything in context, I have the surface of the Earth set up here with the North Pole on the positive part of the z-axis, with the center at the origin, and with the prime meridian intersecting here on the positive part of the x-axis. just convenient setup. Okay, so that said, east longitude is measured like I have here, and then north latitude is measured upward from the equator like that. Hopefully that looks familiar. By the way, of course, you can also talk about west longitude. Everything in the United States is west longitude, right? But so I'm just going to view west longitude as being a negative value of east longitude, and likewise south is a negative value of north latitude. Okay. So with all that said, check it out. Pretty easy pitch just from this picture. Theta is east longitude. Right, with the Earth arranged as I have it indicated here, that's what east longitude is. Literally exactly theta from spherical coordinates. And now, sadly, north latitude is not the same as phi. Phi, again, measured off of the positive part of the z-axis, but a pretty easy relationship. You can notice that these two angles always add up to pi over 2. Right, north latitude and phi is total of pi over 2. Is that satisfying? Everybody see that in the picture? So a couple of easy relationships. Oh, and of course, obviously, the radius of the Earth is rho, and we're going to treat the radius of the Earth as constant. Not really, but whatever. Very good simplification it is. And check it out. We've got spherical coordinates, right? So if you know longitude and latitude, you know the spherical coordinates of any point on the surface of the Earth, which is kind of cool. And I'm going to show you a nice application of that. Here we go. Suppose you work for an airline, and you're going to need to set up a flight from, I'm going to say Oslo, right, to, let's say, Durham, right? So, how far is that? What's that distance? This is a really hard problem if you really think it through, right? You can't use a Pythagorean relationship. You cannot fly a plane tunneling under the ground, right? That's not a thing yet. I hope it never will be, because this would be hundreds and hundreds of miles under. That would be probably, what do you call it, lava? No, what do they call it? When it's under the earth, they call it magma. Thank you. Yeah, I don't want to go down there. You can't make me. So you can also say, well, I could look at a Mercator projection, and I could be like, all right, well, there's kind of this in the sort of longitude direction, and then there's sort of this in the latitude direction, and then you could speculate that, well, isn't this a triangle? Nope, it's not a triangle, right? Certainly not in the Pythagorean sense of the word. So you can't compute the distance that way either. What you have here is a nasty problem, right? Were it not for the trick I'm about to show you, wonderful little trick, wish I'd thought of it. Somebody showed this to me. And the idea is as follows. If you know the longitudes and latitudes of these points, let's just say, right? I mean, that's on any map. You could Google it. There's no problem, right, to find longitude and latitude of certain locations. Well, we just talked above about how to turn that into spherical coordinates. And we just talked on the previous page about how to turn that into rectangular coordinates. Now you know the rectangular coordinates of these points, and if you know the rectangular coordinates, then you can compute the dot product easily. Right? Dot products are really easy formulas in rectangular coordinates. Not in spherical coordinates, not in cylindrical coordinates, right? But in rectangular coordinates, super easy to compute dot product. That means that you can compute this, because that's what the dot product is, which means that you can infer this angle, alpha, and if you think about it, some easy geometry tells you then that the distance that you're looking for is just radius times that angle that you just computed. Right now, there's several little dots to connect, right? And I just swept a bunch of details under the rug, but it's just details, and this little strategy will allow you to compute an answer to a question that would otherwise be very difficult. Does that make sense to everybody? Yeah?
Why does the dot product give the distance between two?
Why does what now?
Why does the dot product give S the distance between two?
Well, it doesn't. The dot product gives me the dot product of the two vectors. Right, I've got the two position vectors here. Dot products relate to angle by way of this old formula. And so the point is, if you know the dot product, you can solve for the angle. And once you know the angle, then that's what allows you to compute the distance. Yeah. I thought that was pretty neato. Couldn't do it without spherical coordinates.
Why does the cross-plot product lead to r squared? Are you assuming that both
It's just the old formula for a dot product. The dot product is
like x squared.
It's the magnitude of one times the magnitude of the other, but each of those magnitudes is the right. Yeah. Okay. Another plug and chug. If you have a rectangular equation and you want to convert that into a spherical equation, it's just a matter of plugging in the formulas. Do look out for nice opportunities, such as this. I can square out that x minus 1 squared term, and when you do so, you get lucky and get an easy relationship to write down, and that saves me doing a bunch of trig that would get me to the same answer, but still, why do I want to have to do the extra trig? It's nice to just be able to easily just plug it in. Okay. All right. Okay, so moving along. Last thing I'm going to say in Chapter 1, and then we're moving on to Chapter 2, standard basis vectors. Very important, of course, to know about the standard basis vectors. These are they. You might know them with this IJK notation. I guess that's fine. I do have a preference for E1, E2, E3 because it generalizes so much more nicely. And again, keep in mind, you cannot just assume that everything's going to be in 3 dimensions. Right? Easy examples of economics problems that we saw first day of class where, 6-dimensional problem. Right? So that's out there. Anyway, these are the rectangular standard basis vectors. They have certain nice features. Among them, they are unit vectors pointing in the direction in which exactly one of the coordinates is increasing and the others are constant. Okay. We can generalize that to other coordinate systems. So, for example, if I'm at, let's say I'm at this point right here, right? Well, I can talk about what is the direction in which r is increasing and theta is a constant. And it's like that. And then I can talk about what is the direction in which theta is increasing, but r is constant. And that's about like that. And keep in mind, I'm talking about r being constant at that exact point. Obviously, the further you go in that direction, r is not staying constant. I'm just talking, though, about at that point specifically. Okay. So, not hard to persuade yourself. A little bit of geometry that these, what we call polar standard basis vectors, have these formulas. So let me just say it's important that you know what standard basis vectors are in, let's say, polar coordinates, and that you know that they exist, and that you know that these formulas exist as well. I also think it's good mathematical weightlifting to persuade yourself. Try to derive these formulas. It's a healthy exercise, right? But I don't have any particular plans to use these vectors in this course. So I'm just going to say, don't spend too much time on these polar standard basis vectors. Yeah.
I feel like I'm not convinced that the red one over there, is going to be a
standard unit vector for the angle? Because it seems as though if you continue that direction, your R is shifting as well.
Yes, it does. But again, keep in mind, we're not continuing in that direction, right? So I just want to know at this point specifically. If you want to talk about at some other point over here, well, yeah, this vector will change. It'll be different, right? And so think about it this way. It's like, what is the instantaneous rate of change of something, right? And so, you could, if you have a curve, right? Let's think back to single variable calculus. If you have some curve, I could talk about, well, at a certain point, the function's not changing at that point. Now it's changing over here. Yeah. But we're not. Yeah, we just want to talk about at that particular point. Is that cool?
Yeah.
Yeah. All right. Okay. So likewise cylindrical, likewise spherical, and we're just not going to do that much with them. So I'm going to point out very quickly. Again, rectangular coordinates are great. Other coordinate systems have some disadvantages. You'll notice from this picture, the standard basis vectors are not constants like they are in rectangular. You don't get nice, convenient relationships like you do here. You have this wonderful relationship between coordinates and linear combinations in rectangular coordinates. You gotta love rectangular coordinates. No such luck in, let's say, spherical coordinates. It just doesn't work, right? So don't overinterpret what these are, but there are some situations where they're useful. I don't anticipate that coming up in this course, but in some future engineering class or something maybe. Okay, so that's a good stopping point for today. We're going to draw the line right here. Y'all have a good one. See you on Wednesday.